Hello everyone, welcome to this lecture of the course Digital Electronics and Circuits, and in this lecture we will be talking about NMOS, PMOS and CMOS. But before we talk about these different kinds of metal oxide semiconductors, let's quickly recall what we spoke in one of our previous lectures on digital logic families. I briefly mentioned in one of the previous lecture that we have different kind of digital IC logic families, one being RTL, one being DTL. RTL stands for sister transistor logic, DTL is diode transistor logic, TTL transistor logic, and this is basically bipolar junction transistor logic. Then we also spoke about emitter coupled logic and MOS metal oxide semiconductor logic, NMOS, PMOS and CMOS, and eventually we have something called as GACS logic. So GAAS logic. So this is like gallium arsenide, right? So these are different kind of major different kind of digital IC logic families. RTL and DTL are now obsolete. These were one of the earliest kind of digital IC logic families. These are now obsolete. TTL is widely used. Bipolar junction transistor is widely used, and as I mentioned in one of the previous lectures, all the 74 star IC series, all the NAND gates 7404, 7410, these are usually made using TTL digital logic families. Emitter coupled logic is also widely used, and this is used for high speed operation. We saw a few characteristics in one of the previous lectures, and I will be briefly touching upon that as well, where ECL is used for high speed operation and gallium arsenide is used for very high speed operations. Our MOSFETs, right, metal oxide semiconductor field emission transistors, these are very compact, which means that density is pretty high, so we can fit in more MOSes in a specified area, and once we can do that we can obtain a better functionality of the systems, and we can build much more complex system using this, correct? And how do we decide that which particular family of IC logic design we have to use? And for that we already spoke about four different characteristics which help us decide which family we want to use, and those characteristics were, if you recall properly, those were fan out, propagation delay, noise margin, and total dissipated power, right? And once we talk about these particular things, we will have to talk about just to briefly touch upon over here, right? When we say BJT operation, bipolar junction transistor operation, this is usually called as bipolar operation. These are like bipolar, and all the MOSFETs are like unipolar. Like, now what's the difference between a unipolar and bipolar, if you ask me, right? BJT, bipolar junction transistor, is called bipolar because the current in a BJT flows due to both electron and hole carriers. So we have like electrons and hole carriers which will result in flow of current, right? Whereas in the field effect transistor, which is like FETs, like MOSFETs, right, the current flows due to either electron carriers or n-type FET or hole carriers for p-type FET, right? That's why they are called unipolar transistors. So this is one thing, like two terminologies which you should be aware of: bipolar and unipolar. Bipolar is a BJT because current in a BJT flows due to both electron and holes carriers, whereas the current in a FET flows due to either electron carriers for n-type FET or hole carriers for p-type FET, and that's why it's called a unipolar transistor. Correct. Now switching gears and coming to what we discussed in one of our previous lectures, and what we did was we drew a chart of characteristics versus different digital logic families. So where we spoke about TTL, ECL, and CMOS, and we characteristics were fan out. It was like power propagation delay. Then we had something like noise margin, and then we have total dissipated power. Power in millivolts, right? And what we spoke was, we said like fan out for CMOS is the best, it's greater than 50, whereas for TTL it's close to 1 to 10, and for ECL it's close to 20 to 30. We said propagation delay for CMOS is bit on a higher side. It's faster for uh, ECL emitter coupled logic, which is like 1 to 6, and it's like 1 to 30 for TTL. Noise margin is pretty high for CMOS circuit. It's moderate for TTL and it's low for ECL. And similarly, total dissipated power was one of the lowest. It was less than 0.01. For CMOS, it was close to 50 megawatts. For ECL, and it was close to 10. So basically, in power dissipation, in fan out, and in noise margin, CMOS circuits are the best. And basically, these are very compact as well. Correct? These are the few properties we spoke about. And now in general, right, what we will talk about over here is, before we look into CMOS. CMOS is nothing but it's like complementary metal oxide semiconductor field effect transistor, right? It's composed of NMOS and PMOS, right? So before we talk about CMOS, let's understand the basics of PMOS and a NMOS, and then we will form a CMOS circuit using this NMOS and PMOS. Correct. Now, if we have to look at a NMOS or a PMOS structure, what we will do is we will draw few diagrams to begin with. Correct. And let's start with a PMOS. So PMOS is something which we represent using a nomenclature which I would be drawing over here. This is something like this. This is usually VDD. Correct. PMOS is something where we put a NOT gate over here. This is my input. This is my ground, and this is where I usually tap the output. Similarly, so basically this is a PMOS, and what is a NMOS and how does it look like? I will draw NMOS over here. NMOS is something like we have an input over here, we have a ground over here, we have a VDD over here, and for NMOS the output is tapped over here. So basically, when I say that output of PMOS is tapped over here, it does not mean that output will be equal to ground always. It will depend upon voltages, different voltages, and what kind of input we supply. Similarly, for NMOS, when we say we tap output at the top, right, it does not mean that output will always be equal to VDD. It will depend upon operation of this particular MOS. Right, in NMOS, this is usually called source, this is usually called gate, and this is called drain. We tap output near the drain for both PMOS and NMOS. So this is usually source, this is gate, and this is drain. Now what happens, right, if we look at operation of these two particular blocks, what would happen? Let's assume that our input, right, let's assume since we are talking about digital circuits, right, we will be only talking about two particular logic level. One is 0, one is 1, right? We are talking about binary operation. Let's call 0 as ground, right, or 0 volt, and let's call 1 as 5 volt or 3.3 volt, right? Let's call them anything else. Let's call anything, right? So basically, now let's assume that we are having a voltage supply, voltage input, or we simply say input voltage, and we will see how PMOS behaves and how NMOS behaves for this, right? Now let's assume I supply an input voltage of 0 volt. So basically, if we supply input voltage of 0 volt, basically if you see, right, one important characteristic which you could simply remember is PMOS. There's one circuit over here, like this is something similar to a NOT gate. What we can say is whenever PMOS a 0 volt input is supplied, this PMOS act as an short circuit. So basically this could be replaced by a wire. It's exactly not a wire, it's kind of a combination of a resistors, and there will be a voltage drop which will be happening through this VDS. What we can do is we can simply assume that this particular block, right, if I have to highlight it and use a different color for this, what we can say is this particular, in this case, it will work like, when we are pointing a 0 volt, this will work like a short circuit. If it works like short circuit, what will be happening is output will be equal to, right, on. Like this will be basically short circuit, so it will behave like on logic, and output will be equal to some high voltage. So basically, let's say it's 1. High voltage will be less than 5 volt or 3.3 volt, depending upon the voltage drop which will happen through this particular MOS. Similarly for NMOS, when we supply a 0 volt over here, right? If we supply 0 volt over here, this NMOS will behave like an open circuit. If this behave like an open circuit, what would happen is my output will be off. Correct? So basically, when we supply 0 volt to an NMOS, this will work like an open circuit, which is like off, and output will be equal to logic 0, which is a logic level low. Now if we supply a high voltage over here, let's assume 5 volt or let's assume 3.3 volt, what will happen in this particular case? In this particular case, my PMOS circuit will act like an open circuit, and since it acts like an open circuit, my output would be off. Like this will act as an off closed circuit, and output will be logic level 0. Similarly, my NMOS, if we supply a 3.3 volt over here, this will act like a short circuit, and this will act like a short circuit, right? My output of NMOS, this will be like on, and output of NMOS would be equal to 1. So this is a basic operation of a PMOS and a NMOS, where we say that NMOS operates whenever input level is high, right? NMOS is acting like a short circuit. And similarly, if that's the case, right? Similarly, if PMOS, when we have an input as 0, only then it acts like a short circuit, and where our output will become equal to 1, right? So this is a basic operation of PMOS and an NMOS, and what we will look at now is we will look at a CMOS circuit, right? CMOS circuit is nothing but it's like a combination of PMOS and NMOS, and let's look at that. So CMOS is nothing but a combination of PMOS on the top and NMOS at the bottom. This is ground, this is high voltage, and this is the output. I mentioned that we will take output near the drain always, and if we see over here, here output is taken near drain, because for NMOS this is source, this is gate, this is drain. Similarly for PMOS, this is source, this is gate, this is drain. Correct? So this is what a CMOS is. It is CMOS comprises of a PMOS and a NMOS. And if we say like this is a PMOS circuit, this is a NMOS circuit. So what we can simply say is CMOS circuit is something like PMOS at the top, NMOS at the bottom, output, and we have inputs over here. Correct? This is how a CMOS circuit looks like. And now let's try to understand a CMOS circuit better with the help of an inverter, right? So the most basic CMOS circuit is an inverter, and if we look at an inverter, it looks something like this. We already know that inverter is one input, this is 0, this is VDD, this is output. Now what happens in this particular case, right? In this particular case, when my input, let's assume my input is nothing but 1, logic level 1, let's assume, which is corresponding to 5 volt. What would my output be? What happens when my input is high? My PMOS will act like an open circuit, and my NMOS will act like a short circuit. If it acts like a short circuit, this output will be equal to 0, which is like a 0 volt. What happens when my input is equal to, it's grounded, let's say logic level 0, let's assume 0 volt. In this particular case, my PMOS will act like a short circuit and my NMOS will act like an open circuit. If PMOS acts like a short circuit, my output voltage would be high. This will be logic level 1, which is like a high voltage. So this is a normal operation of a NOT gate using a CMOS technology, right? And what happens is, like, if we look at this is something like NOT gate we spoke about. Similarly, what we can do is we can draw multiple other gates, like the other basic gates, which is like AND gate and OR gate using a CMOS logic. And if we have to draw it out, right? And similarly, like, we can draw universal gates also, NAND and NOR using CMOS logic. NAND, as we know, is nothing but this is like A dot B whole bar, which is nothing but A bar plus B bar. Similarly, NOR is not of OR, is this one, which is equal to A bar dot B bar. Now, how we can implement a NAND gate is, it's like a pretty simple thing. What we can do is, when we are implementing a NAND gate, let's assume that we are talking about, what we need to have is, we need to have an output where we are simply doing A bar, A dot B whole bar, right, which is nothing but A bar plus B bar. So in such a case, what we can simply do is, we have to use a PMOS circuit and a NMOS circuit. So let's try doing something like this. What we will do is, we will put, correct, what we will do is, we will put two PMOS circuits over here, one PMOS over here, alright. Let's assume this is A, let's assume this is B, and what we'll do is, this is like both of them connected in parallel, and then what we do is, we connect two NMOSes in series, correct, and let's assume this is A, this is B, this is B, right? Now what happens in this particular case, this is connected to VDD. If we tap output here, what happens? Let's put our truth table over here, A, B and C. When my A and B both are 0, what would happen? When both of them are 0, my this circuit would act like a closed circuit, a short circuit, and in such a case, what would happen is, my this, and both of them would act like an open circuit. My this acts like a short circuit, so my output would be a high voltage. Let's assume it was the logic level 1. Now what happens if any of my A, B, right, let's assume my A is 1, B is 0, this is 0, this is 1, both are 1. If both are 1, what would happen is, both of them are off, this is on, this acts like a short circuit and output is 0, this is a low volt. But in case any one, A or B, any one of them is 1, what would happen is, or any one of them is 0, this would, the lowermost, either this will act as an open circuit or this would act as an open circuit. But what would happen over here is, one of these points will definitely act like a short circuit. So in both of the cases, the output would be 1. So this is something like, what we say is, this is NAND gate using CMOS technology. Similarly, if we have to draw a NOR gate, it will be opposite of what we saw for NAND gate, right? NOR gate, in this case, what we will do is, we will connect two PMOS in series, and whereas two NMOS is in parallel. Now what would happen if we do something like this, right? So let's assume this is like this. This is output, this is VDD. Let's assume this is A, this is B, this is A, this is B. Not of OR, right? 0, 0, A and B, and then we have C. 0, 1, 1, 0, 1, 1. Let's assume that when both of them are 1, what would happen in that case? When both of them are 1, this particular circuit will act like a short circuit, and my output would be equal to high voltage, because when both of them are 1, these both are open circuits. So my output will be equal to 1 when both of them are 0. And now when both of them are equal to 1, what would happen is, both of them will act like an open circuit and both of them will act like a short circuit. My output will be 0. And now if any one of them becomes 0, like any one of them becomes 1, what would happen is, either this will be an open circuit or this would be an open circuit. But if any one of them is 1, there would be one short circuit either in via this path or via this path. So my output will always be low. So this is the functionality of a NOR gate. So this is how we were able to realize a NOR gate. using a CMOS technology. One more thing I wanted to tell you about over here is like as we looked at the NAND NOT gate, right? We said like we have a PMOS at the top, NMOS at the bottom, and this acts like an inverter. Usually, right, the upper circuit is something which is called as pull-up circuit, right, and the lower circuit is something which is called as pull-down circuit. And this is usually because this is something which will give the path to conduct or making sure this output is reaching to a low level, and the upper circuit would be helping us obtain a higher voltage by acting like a short circuit. Correct. I hope this lecture was clear. And just to recall, right, to begin with, we spoke about different kinds of IC logic families. We reviewed what are RTL and DTLs being obsolete now, BJT being highly used and it's being a bipolar technology, and then MOSFETs being a unipolar devices. Similarly, we compared different families using a different characteristics, and where we said like CMOS is most widely used because of its advantages in terms of total dissipated power, noise margin, and fan outs, and it being compact. Then we spoke about NMOS and PMOS and how they behave. Why and we spoke about NMOS and PMOS mainly because we wanted to talk about CMOS, which is nothing but it is constituted of NMOS and PMOS together. And once we saw like how PMOS acts like a short circuit when the value is zero, input is zero, and how it acts like an open circuit when the input is 1. Similarly, how NMOS acts like a short circuit whenever the input is 1, and how it acts like an open circuit whenever the input is 0, right? And then we spoke about CMOS logic, where we said, okay, the upper one is a PMOS, the lower one is a NMOS, and then CMOS will consist of PMOS and NMOS. We saw a NOT gate, and we spoke about what are the pull down and pull up functionalities, and then we realized universal gates, NAND gate, and NOR gate using a CMOS technology, and we did a combination of series and parallels to achieve our aim over here, right? Hope this lecture was useful. Stay tuned for the next lectures. Thank you.